Welcome back to this webinar focusing on our e-solutions at Grundfos. As we just examined in the PowerPoint presentation, there is a number of good reasons for why we should choose these e-pumps. But let's just recap shortly so that we are completely sure about why we choose these e-pumps. Well, as we discussed, when we have a hydronic system and we have what we call a system characteristic for the specific system, then this system characteristic can be either rather flat. That's mainly where we have big pipes, or it could also be so that the system characteristic is rather steep, and that is more when we have small pipes. But actually, there's another thing different than the pipe size, which will influence the related pressure loss in the system, and which eventually will give us the system characteristic. As you can see in an application like this, there's a number of different dynamic valves which are opening and closing depending on the actual need in the system and in the building. So actually, in a modern system, even though that the system characteristic always has its starting point from 0.0, the steepness and the flatness, so to speak, can vary. So a system characteristic is not a static thing. But when we know that, then that's also the reason why we have different control possibilities, the different control modes for all of our e-pumps. So let's just recap about what kind of control modes is it actually we have. So let's just redo this one partly. And maybe as you remember we discussed, we had something which we call constant pressure, constant differential pressure actually. Remember that the pump is constantly monitoring what am I delivering in difference from the suction side and to the discharge side of the pump. So when the valves are closing due to these dynamic valves, instead of going up and create more pressure as what a normal pump would do, a non-controlled pump, then an e-pump goes down and follow this line in the same speed as the flow is going down. So what that allows us to do is to put it a little bit modern maybe, is to save this part of energy. When we focus on proportional pressure, you might remember that this is where we have this curve, which is where the pump is decreasing the pressure at times when the flow is going down. And this is exactly the reason for that is that we are trying to adapt to the actual system characteristic for the system. So we get, with the proportional pressure, we get closer to the actual system characteristic, which again will allow us to save another element of energy, which could be illustrated by this area here. But actually in our Magna pumps we have a third option which we have not dealt with before. And I think in order to show you that, we need to make a complete new one, and that is the control curve, which we call auto-adapt. So how this works is, this is typically a control strategy or control mode you would choose in systems where you have very limited knowledge or information about what is the actual pressure resistance in the system. Because what you tell the pump to do is to try to figure out itself how low can we go when it comes to pressure needed for the system. So what will happen is that when the pump reaches the maximum curve here, it will start to decrease the pressure slightly, and it will be in a number of steps, so that eventually it will maybe go down to a pump curve which is as low as this one. And but in order to utilize this or to accept this, what the pump has to do is to constantly monitor that it is delivering the same amount of flow as what it did initially on the maximum curve. Because when it lowers the system or the control curve, what should actually happen with the duty point, it should be on this spot here. So please remember that if a pump is heavily oversized, the auto-adapt function will really not kick in. So in those cases where you think that you have an idea about what is the requirements in terms of pressure, then you could choose to use proportional pressure instead, and then go up front with a lower curve. But that is where we can utilize the auto-adapt in these situations where we don't know anything about the maximum pressure loss in the system. Well, and then further on, we also have what we call flow limit. And that is where we can set a maximum limit to the pump that, okay, we have calculated that this is the amount of cubic meters per hour or gallons per minute we need. So we will accept you to move until this point and deliver this amount of flow, but nothing more. So in cases like this, then we also save this. So in a way, you could say with our new magnet pumps, we have this ability to create the window in which we would like the pump to operate, much more than we have had in the past or in any way. Okay, this was all about the prefabricated pumps with built-in frequency drive, and where there's a bunch of control modes incorporated in the product itself when it's delivered, like the Magnet 3, the TPE Series 2000, so where we have the pump equipped with a differential pressure sensor directly from factory. But actually we have something different, which always sometimes can be a very, very good and neat solution. And let me just make a small sketch for you again. If, for instance, we have a system where we have a pump and we have maybe several meters out to the final consumer out here, and we might have some different users of either cooling or heat until we reach the final consumer out here. And it can be anything. It could be a radiator, air handling unit, or whatever. But if you know where you have what I would call our critical spot or point, that we know that's exactly here. We know exactly what level of differential pressure do we need to deliver out here. Then this knowledge can actually be utilized in order to control our pump in the best possible way. Because what we can do is that we can use what we call TPE Series 1000. And what that does is that if we know, for instance, that we need to deliver, let's say, 20 kPa, 20 kilopascal out here, it's really not that important. Then what we do is that we place a differential pressure sensor out here and send this signal back to the pump and tell the pump maintain these 20 kilopascal out here. Then the pump itself will create its own control curve, so to speak. And then the foot point here for the control curve will be these 20 kPa. And that's actually quite neat, because then it will create this square-formed control curve where we know that in reality, or in real values, we will always maintain the minimum required differential pressure on the critical point, and this pump will always compensate for the friction loss in the system and create its own system or a control curve. So in this case, I would claim that it's a kind of a bulletproof way to control a pump, and our savings will be absolutely maximum. But the challenge about this system, of course, is that you need to have the signal back to the pump, and you need to do a little bit of setup, but it's really not that difficult to do. And sometimes you have like a scatter system or some kind of surveillance systems which will enable you to get this signal after all, and then it can be quite easy to supply the signal to our TPE Series 2000 product. So I think that this could be a very neat and quite a nice way to utilize our Series 1000 product, where we have a very strong solution in order to overcome this question about what is the maximum friction loss in our system. So before we end this session, I think we'll have a short break, and then we'll deal a little bit about the what we call the affinity loss, which is actually the basis behind why it's so profitable of having these e-pumps. But just a short break before we go to that. Well, the last part here, I'll just like to tell you why is it actually it's so profitable to speed control e-pumps. This about utilizing a frequency drive which is built on the pump. Well, the thing is that if, for instance, we look on the what we call the affinity loss, the loss behind speed control, and then we speed control our rounds per minute so that we achieve what we call the half of the flow, then what that will leave us with is that we will get 1/4 of the head, 1/4 of the pressure delivered from the pump. But the real interesting thing is that, and I should have put an H here in front of this at least, but what that will give us is that when we look on the power consumption related to this flow and head will only be 1/8. So that is why it's so profitable and why we should do it whenever possible to speed control our pumps. But we will see a little bit more about that when we go back to the PowerPoint presentation, where you can see it written in another way. And of course you will have all of the materials at the end of the webinar. But thank you for staying tuned so far, and let's head back to the PowerPoint presentation. Thank you for now.